Hello. This is the second part of my talk. The first part was introducing some background and context on arithmetic lattices. And in the second part of the talk, I will talk about where is the geometry. In the second part of the talk, the geometry consists in looking again at these arithmetic lattices, but from the perspective of Margulis arithmeticity theorem. So let me recall what I said in the first part. Margulis arithmeticity theorem shows that if we have a lattice in the real points of a semi-simple real group of higher rank, this lattice must be arithmetic, meaning that it is actually commensurable to the projection of an arithmetic group. That's no good. Just start over. Okay, so now for the second part of my talk, I will talk about the two conjectures. So the conjecture of Margulis that I stated in the first part, and a famous conjecture from algebraic number theory of Lehmer from 1933, still open to this day. Let me start by recalling what I said before, which the starting point is always going to be Margulis arithmeticity theorem, which is this converse to the Borel-Harish-Chandra theorem, stating that arithmetic groups are lattices. Margulis converse states that in higher rank semi-simple groups, this is actually the only scenario, that if you have an an irreducible lattice in the real points of an algebraic group, which is semi-simple of real rank greater than 2, then gamma must be arithmetic. Now, for gamma to be arithmetic means that in this embedding of gamma inside the real points, this embedding is somewhat commensurable to the embedding of the z points inside the r points of some other algebraic group. So one consequence of the arithmeticity theorem was some geometric observation, meaning that inside these connected semi-simple Lie groups, we can find identity neighborhoods that behave somewhat specially with respect to all lattices, arithmetic lattices, which is now an optional term in the higher rank case thanks to Margulis theorem. Now, Kajan Margulis showed that a non-uniform lattice must contain a unipotent element, must contain a unipotent one. But the arithmeticity theorem actually states something much stronger. It states that there is an identity neighborhood such that for any lattice, which is non-uniform and irreducible, then the intersection consists entirely of unipotent elements. Now, let's see how we can conclude this from Margulis' arithmeticity theorem. Now, the arithmeticity states that our group gamma is commensurable with the projection of the z points of some other algebraic group. So we have an algebraic group H, and we have the projection tau from H of R to G of R, and that projection has compact kernel. And in the projection of the z points of H, we have something which is commensurable with gamma. And in fact, in this case, H is Q-simple and the kernel is finite. Now, by construction, if you take the adjoint representation, the adjoint representation of the z point must preserve a lattice in the real points of the Lie algebra, of the real points, sorry. So in fact, it says that at gamma, right, must preserve a lattice inside Lie of G of R. Lattice here means a lattice in the, well, in a similar way anyway, but it's a finitely generated subgroup. So we have a basis of the lattice in which the entries of ad gamma must be integers. Now the characteristic polynomial of this ad gamma must have integral coefficients for any element gamma. If you take now an identity neighborhood which consists of the elements such that the characteristic polynomial of G is half close to x minus 1 to the power dimension of G, which is going to be the characteristic polynomial of all unipotent elements, then you have the conclusion. So it's a very simple consequence of Margulis arithmeticity theorem. Of course, if we try to do this in the uniform case, the same thing does not, we cannot have the same conclusion, since co-compact lattices do not contain unipotent elements. So what is the appropriate conclusion? Margulis conjectured in his book that there's an identity neighborhood such that any irreducible co-compact arithmetic lattice intersect this neighborhood in only elements of finite order. I reiterate that in Margulis' book, there's an assumption of higher rank, but that we actually remove this assumption by simply adding the word arithmetic in such a way that we can include the same behavior for the rank 1 case, because this is really about the arithmetic case. So let's see how we could try to prove this in a way which actually does not go through. So by arithmeticity, we still have that gamma is commensurable with the projection of the z point of some other algebraic group. And this projection has compact kernel. Now, unfortunately, the kernel being compact may not be finite. And this is the case in general. In general, the kernel is not finite. Now, the adjoint representation takes this the z points of G, and this preserves a lattice in the Lie algebra of H. But this Lie algebra now is the Lie algebra of GR with direction with the Lie algebra of this compact kernel. And because of that, because of this compact kernel, the characteristic polynomial no longer has integer coefficients, because we cannot control the coefficients of what happens inside K. On the other hand, what we can say is that if we have an element in H of Z, what we do have is that the characteristic polynomial is the characteristic polynomial for the adjoint representation in G of R times the characteristic polynomial in the adjoint representation of K. Now that has integer coefficients. So we need to be able to control what happens in this characteristic polynomial for the general representation of this compact kernel. This is where we relate this problem to the problem in number 3, which is the Lehmer problem, which is also called the Lehmer conjecture, but there is, I believe, another conjecture due to Lehmer, which is different. And Lehmer himself does not seem to have referred to this as a conjecture. So I do not want to take sides as to whether it's a problem or a conjecture. But let me try to state it. So first, let me define the Mallet measure of a polynomial. If I take a polynomial with complex coefficients, I can simply define the Mallet measure of the polynomial to be the product of the maximum of 1 and the absolute value of alpha I times the leading coefficient C. So it's the product of all the distances outside the unit circle for the roots. If alpha is an algebraic number and it has minimal polynomial P alpha, then the Mallet measure of the algebraic number is just defined to be the Mallet measure of its minimal polynomial. Here are some properties of the Mallet measure. It is a multiplicative map, of course. If we have an integer coefficients polynomial, integral coefficient polynomial, then the Mallet measure must be greater than 1. And so the Mallet measure of all algebraic integers is greater than or equal to 1. What happens for 1, when the Mallet measure is exactly 1, then a theorem of Kronecker implies that we actually have alpha to be a root of unity. So the conjecture of Lehmer is that precisely whenever this is not the case, whenever we do not have roots of unity, then that Mallow measure must be away from 1. But in fact, it should be away from 1 uniformly, so that there exists some epsilon, such that for any algebraic integer, either the Mallow measure is 1, in which case we have finite order, or the Mallow measure is bounded away from 1 uniformly for all algebraic integers. Now, if true, this conjecture would imply a proof of this conjecture of Margulis. And I will try to explain this now. So again, let us recall that if you take an element in H of Z, then the characteristic polynomial, always through the adjoint representation, is going to be the product of the characteristic polynomials in the adjoint representations of GR and of this compact kernel. And that characteristic polynomial has integral coefficients. Now, since K is compact, then the roots of the polynomial PK must actually be roots of unity. And so the Mallow measure of this polynomial must be 1. So despite the fact that we do not know that the coefficients are integral, then we can just pass to the Mallow measure and somewhat get rid of this annoyance. And so Lehmer would then imply that the Mallow measure of the polynomial of PG is equal to the Mallow measure of the polynomial PH, which would then be greater than 1 plus epsilon, or equal to 1. Now, if the Mallow measure is equal to 1, that means that gamma must be torsion, because H of Z has no unipotence from the fact that we have assumed lattice to be co-compact and the Goodman compactness criterion. So now if we can just choose a neighborhood of the identity in G of R such that the Mallow measure is smaller than 1 plus epsilon, where epsilon comes from the Lehmer conjecture, then this neighborhood will be independent of the lattice gamma, and it will work for every possible lattice. And in fact, one can observe that because the degree of the polynomial PG is the dimension of G, and this dimension is fixed in the conjecture of Margulis, then we see that Lehmer's conjecture only needs to hold with a dimension being fixed. So there is an additional simplification of the conjecture that would already imply Margulis conjecture. So let's see how you can weaken this conjecture appropriately. Now, if alpha is an algebraic integer, let me call S alpha to be the number of roots that are strictly away from 1, because these are the ones that matter to me. Now, making the Lehmer conjecture more precise at a level S would be stated as the epsilon coming from the Lehmer conjecture would be allowed to depend on the number of roots outside the unit circle. So instead of requiring that this epsilon be valid for all possible algebraic integers, we will only require this to be true, truncated at some level S. So we will only take into account the polynomials that have fewer than S roots outside the unit circle. Of course, we can look at some specific S, and when S is equal to 1, we have exactly 1 root outside the unit circle. And so in this case, we retrieve a very famous conjecture about Salem numbers, which is that there exists epsilon such that any Salem number is greater than 1 plus epsilon. This is exactly that conjecture, where you have 1 root outside the unit circle for the polynomial. And as a matter of fact, then you must have 1 inside the unit circle, and all of the others must be on the circle. So that's the definition of a Salem number. An algebraic integer with exactly 1 real conjugate greater than 1, and at least 1 of norm equal to 1. So let me give a very brief survey of important results, which are somewhat old, and there are not many, there isn't a lot of progress on Lehmer, although there have been some important contributions in related problems, so problems which are related to Lehmer. But I will not talk about this. So Dobrovolsky has proved a lower bound for this Malin measure, which is allowed to depend on the degree of the polynomial. This bound that we state here for the Malin measure is due to Routier, but it is mostly a refinement of the bound of Dobrovolsky, and this is essentially the same proof. Here's the theorem of Smith. If we take a monic polynomial which is non-cyclotomic, then the Malin measure must be strictly less than the Malin measure of x cubed minus x minus 1. Then, if that's the case, P must be palindromic. Palindromic means that when you read the coefficients from left to right or from right to left, you get the same thing. So the definition is that P of x is equal to P of x inverse times the x to the degree P. Now, keeping the Lehmer conjecture in mind, let me go back to geometry and to short geodesics. So the short geodesic conjecture for hyperbolic surfaces states that there's a universal lower bound for the lengths of closed geodesics in arithmetic hyperbolic surfaces. I forgot the word hyperbolic. The theorem of Neumann and Reed, and also independently of Suri from 92, is that this short geodesic conjecture is actually equivalent to the conjecture on Salem numbers. So what we can say more specifically is that the short geodesic conjecture for hyperbolic 3 manifolds is equivalent to a conjecture for complex Salem numbers. Because the short geodesic conjecture for hyperbolic surfaces only refers to Salem numbers, but the short geodesic conjecture for from the paper of Neumann and Reed includes hyperbolic 3 manifolds as well, and this corresponds to a conjecture for complex Salem numbers. Now, as may be clear already, there is a very neat and beautiful correspondence between the geometry and the number theory, since we construct these surfaces using number theory. And so this is what we prove with François Tilmany. We prove that, in fact, we can generalize this correspondence in a much broader way to take into account all sorts of locally symmetric spaces. So the statement is that sorry, the weak Lehmer conjecture is actually equivalent to the Margulis conjecture in a way that the Margulis conjecture specialized to real rank 1 is equivalent to the Salem number conjecture. And that would be the weak Lehmer conjecture for level S equal 1. So more precisely, we don't even need Margulis conjecture altogether. What we can say is that Margulis conjecture for groups of dimension less than 3s implies the Lehmer's conjecture at level S, which in turn implies Margulis conjecture for groups of dimension less than S. And so this wraps it up and gives us a very clean correspondence and ties the geometry together with the number theory. In fact, with an S given, we can even make this more precise in that Margulis conjecture can be proved. If Margulis conjecture can be proved for one type of groups, or rather one family of groups, then this would already imply the weak Lehmer conjecture. So if you work with Lie groups or algebraic groups and you don't like to work with all the different types, and by type here I mean the Dynkin diagram, then you can pick your favorite one, and if you can prove this conjecture for this particular shape, of particular type of groups, then you will already prove the conjecture for any others. So that means, for instance, if you can do it for SLN, then it would imply it for SPN, SP2N, SON, and so forth. So we get the result for all semi-simple groups. So let me give a quick sketch of the proof. It is an elaboration of both the proof of Suri and Neumann and Reed, together with the construction of arithmetic lattices in semi-simple algebraic groups. So if we take the way we prove this is to prove that the negation of weak Lehmer would then imply the negation of Margulis conjecture. So if we take a sequence of algebraic integers, which are not root of unity, and assume that they are for the corresponding minimal polynomials, the number of real roots outside the unit circle is less than a fixed S, right? Because we work at level S, and that the Mellor measure does converge to 1. Then we will look at this number of roots outside of 1 and fix it actually equal to S, just with a loss of generality. And then we count the number of real conjugates of alpha M. So count the number of real roots. So let's denote this by R. Now, Smith's theorem shows that we can only consider the palindromic polynomials because in Smith's theorem, the Mellor measure is, if it's very small, then the Mellor measure, if the Mellor measure is very small, then the polynomial must be palindromic. So we can only use, we can restrict ourselves to the palindromic polynomials. Now, it means that if alpha is a root, then alpha inverse is also a root. So let me pick an element alpha of this sequence, and let me try to look at its behavior. So let me put Q of alpha and Q of alpha plus alpha inverse to be two number fields. Now we see that because the polynomial is palindromic, then K is actually the fixed field of Q for the automorphism tau, which sends alpha to its inverse. Now, if you fix 2D to be the degree of the polynomial, then we have that the signature of the number field L is 2R D minus R, and the signature of K is R plus D minus S, S minus R over 2. So you just count the number of real places and the number of complex conjugates, number of complex embeddings. And here is the group that I will pick, which is the generalization of the group that I used in my example. We take the special unitary group of the form H to be a K group, and now the automorphism that I use will be tau. So the tau Hermitian form is going to be this form, which is the sum of the xi tau yi, where x and y are elements in L to some power n. Okay. So we have L, we have K, and we have tau. The behavior of this extension L over K will, again, through this restriction of scalar, allow us to give an isomorphism of this algebraic group. So SUH will, in fact, be equal to a product of the algebraic groups. So SLN, and SUN, depending on whether the actual embedding is real or complex or on the unit circle. So it allows me to compute the R points of G as R factors of SLNR, S minus R over 2 of SLNC, and D minus S factors of SUN, which is compact. Now projecting onto the first two, right? I get a group which is SLNR times SLNC, S minus R over 2. So this group here, GSR of R, is going to give me a Lie group, and the projection of gamma inside inside this factor is going to give me a co-compact lattice. Of course, you need D minus S to be strictly positive. Otherwise, it won't be co-compact because you're not modding out by anything. Okay. Now, if you take an element, a very simple element, which is just alpha alpha inverse in the top corner and one everywhere else in the OK points, where alpha is an element of the ring of integers and alpha tau alpha equals 1. So this is the condition that it's in the unitary group. Then pi of gamma cannot be torsion because alpha is not the root of unity by assumption. And now we have this pi of gamma, which is an element inside our Lie group, which behaves accordingly to alpha. In fact, if we can show now that the projection of a sequence of elements gamma m converges to 1, as the Mahler measure converges to 1, then this will be done. And imply that we can find actually elements which converge to the identity while not being torsion, therefore contradicting Margulis' conjecture. And so this is a brief sketch of how to prove the conjecture, in this case for level S, right? So it proves, sorry, it doesn't prove the conjecture, it proves that the conjecture at level S is equivalent to the weak Lehmer conjecture at level S. And the group that we chose is very specific in this case, but is that it does not actually matter because the conjecture of Margulis actually gives us any given semi-simple groups. So in fact, for the sake of completeness, this work can actually be carried for every given type of group. So you can do it for type A, B, C, D for the classical groups, but also this actually works for exceptional groups as well. So it really is about trying to work with some products of Lie groups over R and C, and to reconstruct essentially in the geometry the behavior of the algebraic numbers. So I will end the talk, and this is a very short list of references. Thank you.